Let's have a look at the origin of sine, cosine, and tangent in terms of the trigonometric ratios. I always found it quite fascinating where it all comes from. They're kind of fancy words, sine, cosine, and tangent. But for quite a while, I myself, especially learning it, I thought, it was interesting words, but we sort of just learn it for what it is. But it's always interesting to sort of look it up and think, well, okay, where does it come from? Sine comes from the Latin sinus, which means a pocket. Now, this diagram here, this is what I'm going to be using to sort of demonstrate where the application of sine, cosine, and tangent, and how they all fit together, in fact, especially in relation to a circle. But it's sort of in ancient times, sine actually comes from a word. It's actually a mistranslation of a word that means bowstring, in fact. Based on some of the research that I've done. And you can see the bowstring there. So you can see sort of OB and actually I might put another letter here because I'm not going to use this, but let's call that D. So OB and OD are the bowstrings. OC is the bow. So I've got like a bow and arrow. Sort of, it's sort of kind of holding the bow and arrow, and you're pulling the arrow back to ready to fire the arrow. But let's just see how this all works. So what I'm going to do first of all is I'm going to just measure this angle first, since trigonometry is to do with angles in right angle triangles. So let's put a protractor there and we'll try to sort of estimate roughly what the angle is, and just try to line that up. And I get about 51 degrees. Yep. Okay, so I might just write that in. Okay, so it's only a rough measurement, so there's 51 there. And what we'll do then is that let's measure, and that's a right angle triangle here, by the way. Okay, so that's a right angle there. This is also a right angle triangle here as well, this one, this triangle OBC. Okay, let's measure OA. Okay, so just looking at that there. OA is around 32 millimeters, so I'm just going to put 32 there. Okay, let's measure AB. Okay, so, and you can try this. You can try this with any angle, really. I mean, I just sort of drew something that's sort of quite random. That's about 39 millimeters. So let's put 39. So AB is 39, and the hypotenuse of this triangle, it's about 50 millimeters. Okay, so that's 50 there. Okay, and lastly, let's measure this. Let's measure BC. Okay, so this is what we call the tangent. Okay, and BC is around the 61 millimeter mark. Okay, I think I might have hidden that, but yeah, it's around 60, close to 61 thereabouts. Okay. So that's 61 millimeters there. I think one other measurement that I'm going to just measure is OC, in fact. And OC is around the 70, probably closer to 78 millimeters. Okay, so this is OC. So, okay, so that's 78 millimeters. All right. Now, if we let's look at the three sides of the right angle triangle. If we did inverse sine of, actually I'll see like a calculator there. You can hopefully see that okay. Yep. So inverse sine of 39 on 50, we get something pretty close to 51. So if we round that to the nearest whole number, there's 51 degrees. What about cosine? By the way, if that's 90, that's theta. This angle here is the complement of theta, which is 90 degrees minus theta. That's where cosine comes from, the complement of sine. Complementary angles add up to 90 degrees. So this angle here and this angle here add up to 90. Okay, let's have a look at cosine. Shift cosine, so inverse cos, 32 on 50, and we get something that's pretty close to 50 degrees there. What about tan? So inverse tan, of 39 on 32. And probably, okay, a little bit off here, but it's about closer to 51 degrees, but probably, yeah, okay. So it's between the 50-51 degree mark, so it just depends. So we're only off by a little bit. Obviously, it depends how accurate your measurement is there, okay? Now, the interesting thing is this BC and where this BC comes from. So if we looked at the tangent ratio, okay, the tangent ratio is 39 on 32, okay? And the tangent ratio gives you the ratio of the opposite side to the adjacent side. But if you multiply it by the hypotenuse, you'll get something pretty close to 61. Let's try that. So if we did tan of tan of 39 on 32. In fact, let me just actually I'll do that somewhere else. Okay. So sorry, tan of 50. Let's do tan of 51 degrees for a moment. Okay. Tan of 51 degrees. Okay. And if we multiply that by 50, okay, let's see what we get. Tan of 51 degrees. Multiply that by 50, and we get 61.7. So probably closer to 62, which is roughly equal to this value there. And that's actually why it's called the tangent ratio. It's because it's related to the tangent to a circle. In fact, BC is a tangent to this circle because it only touches the circle once, and that's what a tangent is. In fact, if you ever hear the word or see the word tangent in mathematics, so if there's a, for example, if there's a, actually I might just do it here, if there's a curve, for example, I could draw a tangent to that curve. It just means that the tangent only touches the curve at one, just at one point, sort of locally, you know, sort of around that little area there. Likewise, BC is a tangent to the circle, and that's actually one of the reasons why it's called the tangent ratio. One other very important measurement, and I thought, and then we'll end the video there, is this last one here, which is OC. Now, OC is the arrow, the sort of the arrow part of the bow and arrow. And when we measured it, it was roughly around 78. Now, that's called the secant ratio. That's called the secant. So, okay. So OC. Okay, it's called a secant. Okay, and that comes from Latin as well. And secant means to cut. So OC cuts the circle. So it cuts the circle there. It's not a tangent, but it cuts the circle at a point that's very different to the tangent. In fact, if you continued OC along to the other side, in fact, it would cut the circle to the other side. In fact, it would be the diameter of a circle, but it would kind of continue on. So that's why it's called a secant. In fact, anywhere else, if I was to draw sort of a line like that, like a chord that sort of extends beyond the circle, that's also called a secant as well, because it cuts the circle more than once. Okay, so where does this come from? So in trigonometry, the secant is in fact the reciprocal of cosine. In fact, let me just see if I've got some space here. So in other words, 1 on cos theta is in fact equal to what we call the secant, right? Sec theta. Okay, so let's see how this works here. If cos theta is 32 on 50. Okay, actually it's just slightly off there. I'll just move it over a little bit. So just make sure you can see that. Yep. All right, so cos theta is equal to 32 on 50. Okay. Sec theta, the secant of theta, okay, which is 1 on cos theta, is 50 on 32. Okay, so that gives you a ratio. Okay, so this is a very important number. Now, 50 on 32, we're going to multiply it then by the hypotenuse, and it should hopefully give us something pretty close to the length of OC. So 50 on 32, multiply that by the hypotenuse of 50, and let's see what we get. Okay. So 50 on 32, which is the secant ratio, multiply it by the length of the hypotenuse, and we get 78.125, or thereabouts, which is roughly the length of this secant here. And that's actually why the reason why it's called secant. In year 10, you don't really look at that. You tend to look at that in year 11 and 12. So, but it's just something that's interesting there. And it's nice to know a little bit of history about the origins of sine, cos, and tan. So, hope you enjoyed the video, and all the best for your studies.